Alright, kia ora everyone. Let's get started then for our lessons for the week 5 lockdown. You only have 2 lessons of content this week to help you guys kind of know what is expected to be done. I've tried to outline here basically what week this work is for, and then over here I try to give you guys a total of how many lessons you're doing this week. So this week I only have 2 new theory lessons for you guys. I'm trying my best to kind of pair it so that way each week is kind of like a nice chunk of information. It's kind of themed, and you guys then also have plenty of time to work. So, like I said last week, we're moving on to the second half of the next chunk of information, which is all looking at the forces and phase changes. So this first lesson for this week is going to be on exploring the attractive forces between covalent molecules and how it affects their properties. Like I said when we did our first lesson for this section for types of solids, the main focus for this year is going to be your covalent molecules. So let's your covalent molecules, and basically looking at the intermolecular forces that hold that solid together. So on our checklist today, you guys can tick off number 4 and number 5. So number 4 is explaining those attractive forces, and number 5 is explaining their properties. The ones that they'll probably be highlighting is the melting and boiling point and the solubility. Cool, so let's talk about the forces between molecules and kind of refresh some of the vocabulary from last year. Before I do that, I just want to remind you guys to be really careful of your terminology. Even though we're talking about covalent molecular compounds, the bonds that we're talking about when we're thinking about phase changes and their properties is going to be the intermolecular bonds. So the intermolecular bonds are the molecules between the molecules. Remember, molecules are going to be making up this type of solid. The intramolecular bonds are the covalent bonds between those two atoms. When we are talking about these properties and these phase changes, these are not the bonds we should be referring to. We should be referring to these ones over here, and that's going to be the focus for the next kind of 2 lessons. A lot of the properties then for these covalent molecules really depend on the strength of this bond here. Now these are generally pretty weak bonds in comparison to the grand scheme of things, but they do vary, and that small variation results in some very different properties. This is known as this is a force of attraction, which is the result of electrostatic attraction. Again, it all ties to that positive and negative charge. We'll look at some specific examples of where that's going to arise from. When you guys are thinking about vocabulary words, they're not going to be too picky, but if you do want to be careful and get yourself up to that excellence level, you should be referring to these as forces and not bonds. Force is a more accurate description of what it actually is, whereas bond is a more accurate description of talking about between atoms. In the covalent molecules, we have to remember that they have electron clouds surrounding those atoms. Electrons are also being shared between atoms, and therefore those electrons may not be evenly distributed. And if they're not being evenly distributed, what you're going to have then is a separation of charge, basically creating a dipole. And we talked about this in the previous lesson when we're talking about the polarity, and polarity will come into play when we're thinking about these questions here. Since these electrons can be distributed unevenly, what's going to happen is those electrons can be in one location or area of the molecule, resulting in it to be slightly negative, and then the absence of those electrons means that that's going to be a slightly positive end. And because we have an unequal distribution of charge, that molecule and the molecule next to it are obviously going to have positive and negative, and then the positive side of one molecule will be attracted to the slightly negative side of the other molecule, allowing then for those intermolecular forces. So let's talk about the different types of dipoles, which is going to interact then with the different types of bonds we have. So the first type of dipole we will have is a temporary one, and basically what can happen is we can have an attraction between 2 temporary dipoles, known as then a temporary dipole-dipole attraction. We can also have attractions between permanent dipoles, so that's when the dipole is always there, and we call that attraction between two permanent dipoles, a permanent dipole-dipole. The last type of intermolecular bond that we'll be talking about is a hydrogen bond, which you guys have visited last year. Be mindful that last year you did talk about these things. We just talked about them in a very general sense of intermolecular bonds. Now we can actually go and talk about the specifics behind them. So the first one I want to talk about is that temporary dipole-dipole force, interaction, attraction. And basically, this is the attraction that you get between two nonpolar molecules. So even if both molecules are nonpolar, they're still going to have a force that holds them together. However, this is a really weak force, so generally our nonpolar molecules tend to be found in gases unless this temporary dipole-dipole interaction is really, really strong. But this is a universal force that you see. It's not just limited to polar molecules. You will also see this this is not just limited to nonpolar molecules. You'll also see this in polar molecules. This is the result of the electrons being in constant motion, and then just by chance, they happen to congregate on one side of the molecule. This creates what's known as a temporary dipole. So this is not a permanent location or distribution of the electrons. It just happens to, by chance, kind of congregate in that area, causing it to be slightly negative, and thus the other side being slightly positive. So this is a totally random event, and it's not, like I said, permanent. It's temporary. It just happens, and then it'll move. Then the electrons will move again, and the dipole will no longer exist. The thing is that when one temporary dipole is created, it can influence atoms, or I should say molecules nearby it, and it will force the other molecule to also form a temporary dipole. And that's because in this case we have one end of the molecule that's slightly positive, and so that's going to attract the electrons of another molecule, pulling it closer to there and inducing it to become a temporary dipole, thus forming our temporary dipole-dipole interactions and the bond that attractive force that's now present. So the next thing to then think about when it comes to inducting a temporary dipole is basically how easy it is to distort the electron cloud, which is known as polarizability. Can't pronounce that word. It's just that force of attraction to create a temporary dipole. When it comes to the trends and patterns of this will increase the larger the atom is. And this is because there are more electrons present. So since there's more electrons present, it's more likely then to get that unequal distribution of charge. There's lots of electrons there that can then be influenced to then pull into a different direction. So basically, you have your first original temporary dipole that forms, and this is now going to be attracted to the neighboring molecule, forcing it to also form a temporary dipole, basically inducing it to become a dipole. So larger atoms will have a stronger force of attraction between molecules because there are more electrons there that can then move to form this temporary dipole. So we can see this in the trend when we're looking at, in this case, the haloalkanes. This I have seen as quite kind of a common question, maybe not necessarily in the graph form, but they do actually have you compare and contrast molecules in the same group. And as you can see, as we go down the periodic table and these atoms become larger and larger, the melting and boiling points become higher and higher. And that's just because they're larger atoms, more likely to then induce that, more likely to form and then induce temporary dipoles. The other thing that will factor into temporary dipole and the strengths of them, or how many there are, is going to have to do with the shape of the molecule. So shape of the molecule is really important with that influence. The reason is because of the stacking properties it has. So basically, how easy is it to kind of stack layers of these molecules on top of each other? And I believe we've talked about this last year when you guys were looking at organic chemistry. Basically, the more linear the shape is, the easier it will be for these guys to stack on top of each other. There's going to be more cleanness when we're trying to do those intermolecular bonds. As the molecule becomes more and more branched, it's a lot harder to stack these on top of each other. There's going to be less intermolecular bonds. There's going to be less interaction for those temporary dipole bonds. And so what we'll see is as it becomes more and more branched, the melting point and the boiling point will drop. And basically, the more spherical that molecule gets, the less likely it is to be able to get close to another molecule. And like I said, referring to kind of that stacking property. Again, they often ask this question where they'll give you two molecules of the same molecular weight, basically same molecular compound. It's just a structural isomer, and that structural isomer will have more branching than another one. Like I said, very, very common question. So that then wraps up the temporary dipole interactions. Now let's move on to the permanent ones. These tie really well then into what we were talking about with polar and nonpolar. So basically, permanent dipoles are what you'd expect. They are permanently going to have that unequal distribution of charge. And when we're thinking about unequal distribution of charge, we are thinking about polar molecules. This molecule will always have a slight positive and a slight negative end. So that's what you're looking for when you're looking for stuff that has permanent dipole-dipole. They often tie this question into the polarity question. So you might first identify which molecule is polar, which molecule is nonpolar, and then you would talk about what intermolecular bonds they have to explain their melting and boiling points. But do keep in mind that polar molecules will still have temporary dipoles present as well. You'll be talking about how they have both of them. And since they have both of them, that's again going to make more intermolecular forces, and you're going to need more energy to then break all those bonds up and thus change the phase. So polar molecules will have higher melting and boiling points compared to anything that's nonpolar with the same molecular mass. And they often like to compare things of the same molecular mass because then they're going to have the same number of electrons that you're working with those electron clouds. So that's not going to be a factor into the boiling and melting points. So not only are there more forces to break, but also that permanent dipole-dipole bond is stronger than the temporary dipole-dipole bond, and all of this is going to require more energy to break them, and thus higher melting and boiling points. The last example then is the hydrogen bond, which you guys talked about last year. This falls under the category of a permanent dipole-dipole bond. It's just a special one because it is exceptionally strong. And there has to be really specific conditions to make that hydrogen bond. Basically, I need a hydrogen atom attached to something very electronegative, fluorine, oxygen, or nitrogen. Hydrogen, you have to remember, is a very small atom. It only has one electron, and when it's covalently bonded, it has two electrons. If I'm attached to something very electronegative, it's going to pull those electrons way closer to it, to that electronegative atom, and then it basically exposes that proton nucleus that hydrogen has. Because remember, hydrogen would only have that one proton there. So that makes it really, really positive. So that's, like I said, exposing that nucleus. The other thing you have to remember is that hydrogen, nitrogen, and fluorine all have unpaired electrons. So that makes it, again, very negative in that area of the molecule. And so what's going to happen then is you're going to get this attraction between these electron-negative atoms that have lone pairs of electrons that are, stealing those covalent bonded electrons, and then they're going to be attracted to that positive nuclei, which is basically an exposed nucleus. And that is my hydrogen bond there. So like I said, it is just a type of permanent dipole that's really sort of specific. But it's very, very strong force. So that's going to, again, like I said, require that bit more energy to break it. So basically, again, keep that in the lookout when you're looking at these molecules. Are there any potential for hydrogen bonding there? And that's going to greatly influence its melting and boiling point. Just as a fun kind of thing to kind of tie in, thinking about ice and why ice floats on top of water. This is the structure of water when it's in the liquid form, and this is when it's in solid. basically what happens is you're going to have these hydrogen bonds form between our water molecules, and it forms in a very rigid lattice, resulting in these air pockets. And these air pockets are what makes ice less dense than water, and then it can float on top of it. So I just thought that was kind of neat information to know. All right, Kapai, that is our first lesson of week number 5 done. So just to recap, you guys should be able to explore those attractive forces between covalent molecules, and then how does that link into their properties. So remember, we've learned 3 of them. They're the temporary dipole-dipole force, there's the permanent dipole-dipole force, and then there's the hydrogen bonding. Now, if you guys are wondering what should I do after this video lesson, just go to the Google site and click on the link, and there's a whole list of recommended tasks for lesson number 11, which is forces between molecules. Like I want to remind you guys, you don't need to do all those tasks there. They're just there so you have a variety of choices based off of where you are in your cell-wise kind of process and learn this material. Anything that you do, can you please make sure that you write your answers or you insert images of your written work into the Google Doc that says evidence of week 5 lockdown work, so that way your teachers and I know you've done some stuff for this week. And as a final note, if you're in my chemistry class, can you please make sure you do your weekly check-in? I still want to keep in these habits. I think they're really good, and I will be reading them just to kind of check in on you guys. You want to fill in week number 5, think about what your micro goal for this week is, recap what you learned last week in chemistry, a little space if you need to tell me anything. Don't worry, you can leave that blank if you want. And then our random question for this week is, who is your favorite band or musician? I haven't had a music question before, so I figured that'd be kind of cool. Anyway, that's our first lesson done.